You're welcome to this electrical and electronics course. This course is meant for all engineering students, enthusiasts, and all those that are in the profession. So in today's tutorial, we'll be talking about current. I'm sure as engineering students we are all familiar with this term. Current is simply the movement of matter past a given point with respect to time. Okay, what do I mean? It's not only electrical current. Yes, I know you really want me to talk about electrical current, and that's exactly our focus in this course, but we are going to first of all define current just as it is. Okay, so like I have said, current is the movement of particles past a given point with respect to time. Okay, so it's just a movement of particles. That movement of particles is what is referred to as current, because we know that time is obviously present in each and everything that we do. So the movement of a particle is what is referred to as current. So we've got a number of examples on current. I'm sure if you have done your grade 7 well, you understand that we learned of ocean currents. Okay, so e.g. we learned of ocean currents, and we also learned of that was in secondary school, obviously, for many. We learned of electric current. Okay, so now our focus in this course is electrical, or rather electric current. Okay, so this is how we are going to start this course. So now, what is electric current? What is electric current? Okay, so obviously this is a question that must pop up as at now, defining what electric current really is. Okay, so quite a good question that one would ask. We all know that somehow this very current is what leads us to having power in our homes, in the industries, in our workplaces. I mean, by now it's obvious that we really cannot do without power, and because of electricity we have come to develop a number of things. Okay, we have come to develop the health sector, we have come to develop any other field that you may think of, because many of these fields can't do without electricity. Agriculture, for instance, also has been developed because of electricity. The use of those machines on the field require electricity for them to work. So what actually gives us this electricity? It is the current which we are talking about today. Okay, so the question obviously here must be, what is electric current? So now before I even try to explain into detail what electric current is, I'm going to talk about some few things that you are supposed to know. Okay, so now for you to understand how a current really works, you need to have the basic knowledge of three things. Okay, what are these? These three things are: number one, conductors. Okay, then number two, semi-conductors, and number three, non-conductors, or like we call them, I'm going to use this word that will interest you for now: dielectrics. Okay, the page is not big enough for me, but yeah, so now it's big. So dielectrics. Okay, so for you to understand what current really is, you are supposed to know these three things. Okay, number one, conductors. Number two, semiconductors. Number three, non-conductors. Okay, so what are, because you notice that in all these three things that you're supposed to know, the most common word that is there is conductor. Okay, conductor. Even here we've got conductor. So what are conductors? All right, so you will agree with me that we have learnt of this in primary or even secondary. Conductors are simply materials that allow electricity to pass through them. Okay, so as I have said, conductors by definition are materials that allow, okay, electricity to pass through them. Okay, my handwriting is not as good as you would want it to be, but this is where we are. So conductors are materials that allow electricity to pass through them. Okay, so now other than conductors, we have got semiconductors. Semiconductors behave like conductors and at the same time like non-conductors. So you know that if conductors are materials that allow electricity to pass through them, then non-conductors, which is what I've written here, non-conductors are materials that do not allow electricity to pass through them. And the ones which are found in between these two, the conductors and the non-conductors, are semiconductors. Semiconductors are materials that at one point in time would allow electricity to pass through them, but at the other point in time would not allow electricity to pass through them. This depends on the amount of heat that you apply to them. That is what determines whether these materials conduct or don't conduct. But our focus for now is the conductors. This is what we want to really dwell upon, because for us to understand electricity, we need to understand what allows electricity to pass through them, which are the conductors. Okay, so to just explain more on these conductors. Conductors generally, we know them to be materials that have got free electrons. Okay, just keep it simple. Let me say conductors are usually metals, unless otherwise, unless these other gaseous materials or plasma like materials that may exist, and that is not our focus right now. Our focus for us for now is just to talk about conductors, which are metals. Okay, so you understand to say every material will have an atom. Okay, every material is an element that has got atoms, and an atom by definition is the smallest particle of an element, okay, that can exist in that element. So now let us take it this way. We are going to utilize metals, and the most common of all metals are wires that we use. Okay, so we are going to explain the electricity conduction in this sense. Okay, so wires are materials, or wires are elements that have got atoms in them. Okay, and because metals are materials that are able to conduct electricity, so metals have got atoms inside of them, which are the smallest particles that may exist, and that right now is really not our focus. What I'm trying to make you understand is how these metals are come to conduct electricity. Okay, so if we consider a metal at its atomic level, So as I was saying, if we consider a metal at its atomic level, we will have something that looks like this, and I'm sure many of you guys know this. Okay, so I was saying we are going to have something that looks like this, and then inside this we're going to have these little things. Okay, and then along on this very line, that is the outer line, we are going to have things that look like this, which are obviously electrons. Okay, so now metals have got this kind of atomic design. Okay, so what are these small these round drawings inside here? Okay, what are they? So in here is protons, rather, which are represented by P, and neutrons. Okay, and that is really not our focus right now. Let me emphasize this point. And these protons and neutrons are found inside the nucleus. All right, the nucleus. So this is just the atomic structure of every metal that you can have, every wire that you can have. At its atomic level, this is what exists. So you've got electrons on the outer shell, and then inside the nucleus is where you're going to have the protons and the neutrons. Okay, so protons, we all know, are positively charged. Neutrons have got a neutral charge. Electrons have got a negative charge. Okay, so this is just the atomic structure of every wire that you can have, every wire that you would like to use to conduct electricity. So if you want a wire to conduct electricity, you will need to have free electrons, and you also need to have bound protons and neutrons. Okay, so now what do I mean by this sense? Assume that we have this simple circuit. Okay, let me just draw it down here. Assume that we have this simple looking circuit. We'll have a battery here, okay, and then we'll have a wire. Okay, don't mind my drawing. What I'm trying to show is the little things that happen inside that wire. So my drawing of the wire is going to be a bit bigger than it normally is. Okay, so this will be your wire. Let me just show the demarcation there, the difference between the battery and the wire. So this is going to be your wire. Okay, so this is your wire, which completes the circuit. All right, so for you to have current flowing, don't mind my slip of the tongue. So for you to have current flowing in this circuit, you will need to have electrons. It is actually a requirement that electrons are free in that material through which current is passing. And like we said, all metals are conductors, okay, unless otherwise, but all metals are conductors. So in these metals, we all know that the electrons are free. Okay, they are put into a pool of electrons that allows them to move around whenever they come into contact with either an electric field or a magnetic field. But in this case, what we have is a battery. So this battery is actually giving rise to an electric field. Okay, it is actually fulfilling electric current flow. So now what happens in this scenario is we'll have majority of electrons in this very battery. Okay, this battery is going to have excess electrons that are, by design of this battery, experiencing a certain pressure. Okay, so every battery is designed to have a lot of electrons inside it and a lot of pressure backing up those electrons. Okay, the manufacture and the science behind this is what you really don't need to know as at now. You can know it as we proceed in our course, but all you need to know is that inside a battery there are excess electrons that have got an excess amount of pressure that tries to force them out as you connect a wire across its positive and negative terminal. So if we look at this battery I've drawn here, this battery, we are going to see that there is one side of the battery which is positively biased or charged, and then there's the other side of the battery which is negatively charged. Okay, so now what happens in this sense is that because we have said inside the battery are electrons that have got excess electrons that have got excess pressure, and this pressure tries to force them out when you connect a conducting material across its terminals, across its negative and positive terminal. So once you do that, once you connect conducting material across its terminals, you are going to have these electrons being pushed out of the battery into the conducting material. And as we have said, at an atomic level of a conducting material, you are going to have electrons which are free to move, but protons, or rather positive charges, will be bound. So in this drawing I'm only going to consider those charges that are free to move, which are the electrons. Okay, so the drawing in white are electrons that were initially in the wire. Okay, so consider that the drawings in white, this drawing that is in white is a representation of the electron that was initially in the wire, not the electron that is coming outside the battery. Okay, so as that electron coming outside the battery gets into contact with the electron that is in the wire, there will be a force of repulsion. As you can see, these two charges are like charges, and according to magnetism, because electricity is actually born from magnetism, so according to magnetism, like charges repel while unlike charges attract. So these two charges, the electron that is coming outside the battery and the electron that is in the wire, they will experience a force of repulsion. But after this force of repulsion takes place, what will happen thereafter? And this is where I want you to get the science that takes place. Okay, so now I'll need you to pay attention to the science that takes place here. So let's say this electron that was in the battery comes out of the battery and gets into the wire. Okay, so its initial position was here, but then its final position is here inside the battery. Okay, so once this electron that has come outside the battery meets the electron that is inside the wire, there will be a force of repulsion because these two charges are like charges. Okay, so now once there is a force of repulsion between the two, here is where the case of only the strong charge, only the strong negative charge will be moved. Okay, and in this case it won't be the charge that has the negative charge that has come from the battery, because the negative charge that has come from the battery has got a force that by design of the battery is causing it to push other electrons, to oppose and defeat other electrons. Okay, so in this case, when this battery releases this electron, this electron will meet the electron that was in the wire, and because the electron that has come outside the battery has got a larger force that is backing it up, it will force the electron that is in the wire to be repelled, okay, to move towards the positive side of the battery, or the positive terminal of the battery. So this electron that is in the wire will be forced to move in this direction. Okay, So as I was saying, these negative charges that are in the battery, when these negative charges are forced outside the battery because of the pressure that they experience, they'll move outside the battery and go into the wire. And in this wire, like we have said, we've got electrons that were initially free but were not moving. They were free to be biased by any field, by a magnetic field or an electric field. That was their initial state. Okay, so when these electrons that are come outside the battery, which are these here, this which is this representing many electrons, so when these electrons come into contact with the electrons that were inside the battery initially, there will be a force of repulsion, and only the electrons that have got a weak backup force will be forced to move. Okay, so in this case it is this electron which is in the wire which will be forced to move because it has got no external force that is backing it up. Why? Because it has not come outside the battery. It was initially in the wire. It was only free. There was nothing moving it initially, but because it has come into contact with this other electron which has come from the wire, which has got a negative pressure which is forcing it, which is backing it up, it will cause a force of repulsion between the two, and only the weak electron will be forced to move away, to move away, to move away in this direction that you see it moving. Okay, so as this continues to happen, it gets to the positive side of the terminal, runs through the battery, and the movement continues on and on and on and on. Remember, as the electron is moving, because electrons are what are the particles that are free to move in a conducting material, whilst the protons or the positive charges are bound. Okay, it is considered that only electrons move in a wire. That is by electron current. We'll discuss electron current and convection current later, but for now let us understand that in a wire it is electrons that move and not protons or positive charges. Okay, so now we get to define what really is electric current. Okay, so to just define this, before I even write up something on the definition of electric current, let me just draw something that looks like this. So as I was saying, to define electric current, we need to use this analogy that you are seeing on your screen right now. So now this analogy, in this analogy I have used this simple diagram of a syringe. I hope we all know what a syringe is. Okay, a syringe is simply that plastic item that the doctor uses, where he attaches a needle on one end and then a syringe on the other, and he uses that for injections, if somebody out there doesn't know what a syringe is. So basically that is a syringe, and that is what we are using in this drawing. This is a drawing of a syringe that's here, trying to represent or trying to show you the analogy of electric current. So in this drawing, and if I can try to refer to the diagram that we just drew, the EMF, this which you see here, the EMF is the pressure that was inside the battery. Okay, so the EMF will be the pressure that one will use to apply to this one end of the syringe. Okay, and we also have some red drawings here, some red circles with dashes inside of them, and these red circles are actually the charges or the negative charges that's inside the wire, that are initially inside the wire. Or in other terms, if we look at it in the term of just the syringe, and this can be said to be the water inside the syringe. Okay, and then one other thing that we have is the flow of this water outside of the syringe, and this is what we are referring to as the current. Okay, and because this is what we're trying to define, I'm going to try and compare this diagram and the actual electric circuit diagram. Okay, let me just show you that in a bit. Okay, so in this drawing that you are seeing down here, this is a drawing that is being compared to the analogy that we have used on top. Okay, so the pressure that one would apply on this end is actually the pressure that will be found in the battery. Okay, and always remember this: the EMF of a battery is a force that acts upon the charges, the negative charge, or rather the electrons in a wire. Okay, so let me just write that down. EMF so EMF is simply the force that moves electrons, hence the name EMF. And if you don't know, EMF stands for electromotive force. Okay, so electro meaning electron, motive meaning movement, then F, which is force, meaning the force that drives these electrons, hence the name electromotive force. Okay, so now, like we have said, this EMF in the circuit that we have drawn here, the EMF which is in the circuit that we have drawn here is similar, or is representative of the force that one would apply on this one end, okay, of the syringe. So once you apply that force on this one end of the syringe, that force will be exerted. It will exert a certain pressure on the charge, the same way the EMF in this battery would exert a pressure on the electrons in the wire. Okay, like we discussed in the previous diagram that we did on the circuit. So like we are saying here on top on the syringe, let's try to go back to the syringe. So here, so when you exert this pressure or the EMF, this force will exert a pressure on the water or the charge that we have inside this syringe, and once this charge starts to move, we'll have a current flowing. Now, one thing you must remember is that a current will never flow where there's an open circuit. If we assume that this was open here, there cannot be a current flow, contrary to what you are seeing here. Yes, there is water flowing in the syringe analogy, but we just try to use this analogy to explain what really happens inside the wire, but don't consider the flow, because this flow of water or the current, it needs to be continuous for it to be referred to as current. So for now, let's try to remove this and start to look at the real thing that we are talking about. So the real thing here is what is down here, the current. So now, as I was saying, current will never flow where there's an open circuit, where there's no closed circuit, where there's no connection between the positive terminal of the battery, which is this, and the negative terminal of the battery. If there is no complete connection between these two terminals, then current will definitely not flow. That is one thing you must understand. Okay, so now that we are done trying to understand the previous drawing, the previous diagram that we did, we can now safely say that electric current is simply the movement, or rather the flow of electric charge past a given point in a complete circuit, in a closed loop or a closed circuit. Okay, so let me just write that down for you so that you do not forget what we are talking about. So electric current. Okay, so just using the drawing that we have done here, where we have the battery and the lamp and the connecting wire, it is now safe for us to say that an electric current is simply the movement or flow of charge past a point in a closed loop per unit time. Okay, what do I mean? In every complete circuit, in every circuit that has got components connected together with conducting material or conducting wire, you are going to have a current flowing when you apply a voltage or a force or an EMF to that circuit. Okay, so like I'm saying here, electric current is the movement or flow of charge past a given point in a closed loop. So because the circuit that we have like on top here is a closed loop, and we've also applied a battery which is a source of EMF, a source of force to this charge, we're going to have an electric current in this closed loop. One thing you must understand is that current does not flow. It is the charge that flows, and this flow of charge is what is referred to as current. I will repeat that again. Current does not flow. Don't be misled by people who are always used to saying that current is flowing, current is flowing. Current really does not flow. Current is the actual flow. Okay, it is the flow of charge. It is the charge that flows and not the current. It is the charge that flows in a closed loop that gives rise to a current. And to conclude on this, using this same information I've just talked about, it is safe enough to conclude with this formula on this side. So we're going to say current, which is represented by I, is equal to the charge per unit what? Per unit time. And the unit of measurement, the SI unit of current, is the amp or the coulomb per second, because the charge is measured in coulomb and then the time in seconds. So it can either be coulomb per second, that's the unit. The unit can be coulomb per second or the amp. Okay, the amperage. Okay, so this is basically what current is all about. And so to just summarize everything that we have done, we have talked about metals being the backbone of electricity, because we use metals for us to be able to have electricity. Okay, we're supposed to use conductors, and conductors usually, most commonly, referred to as the metals. Okay, so we use metals to conduct electricity. Okay, and we have talked about their general atomic structure. Okay, that is what we have talked about, a general atomic structure. We have said that the positives or the protons are bound in the nucleus, they don't move, but it is the electrons or the negative charges that move. Okay, or they are not bound to the nucleus. So because of this movement of this freedom that the electrons have, when met with an electric field or a magnetic field, these electrons are able to move, and if the path through which these electrons are moving is complete, we are ultimately going to have a current flow. Okay, so that is what we have talked about. And one other thing also that we have talked about is current. We have defined current in its totality using some diagrams and some illustrations. Okay, so from what we have done so far, one thing that you must understand is that in a complete circuit, it is the charge that flows. Okay, it is the charge. So this is just a diagram that is showing a piece of wire. We are going to assume it is connected. It is connected to a battery or any voltage source. So in this piece of wire, it is the electrons that move. Okay, the electrons that move. Okay, whilst the protons are bound, they don't move because they are bound with a neutron in the nucleus and all of that, but that is not what we want. So one thing you must understand is that the electrons are moving in this wire. Once you expose this wire to a voltage source, these electrons will start to move, and the movement of these electrons is what is referred to as current. Okay, and one thing that I must always emphasize, I emphasized and I will do it again right now: current does not flow. Okay, current is the flow of charge. Okay, it is the charge that flows. These negative charges that we have are what are flowing, and this flow is being referred to as current. Okay, so it is not the current that flows, but it is a charge that flows. Bekami vapor, I'm using vernacular now. Bekami vapor, that it is current that flows. It is the charge, the negative charge, or the electrons that flow. And why do these electrons flow? Remember, we have said this wire has been exposed to a battery, which is a voltage source, and inside that battery is the EMF, and the EMF is simply the force that gives, or rather makes, the electrons or the charges move. Okay, hence the name EMF, and this stands for electromotive force. Okay, so this is the EMF. Okay, so EMF causes the charge to move. It forces the charge to move, and this movement of charge is what is referred to as current. Okay, so thank you for watching this video. See you in the next video.